So, in this second part of Chapter 8 practice, we're going to associate the heat energy to the chemical reaction and to our concept of stoichiometry. Okay, so we're going to basically expand our mole recipe. So let's take a look at the first problem now. We have a 15.0 gram sample of coal that is tested by bomb calorimetry, and upon combustion the sample release 4 points. So the energy is released. If the energy is released, the energy goes out of the system. Okay, so we're releasing 334.5 kilojoule of heat, and we want to know what is called the fuel value. So let's take a look at the unit. Very simply, we have kilojoules and we have gram. Therefore, the fuel value for this blend will be equal to the energy released, 334.5 kilojoule, over the mass of the sample, because 15 gram released this amount of energy. Here you find your units for the fuel energy, and to 3 sig figs we get 22.3 kilojoule per gram. What is very important to understand is the meaning of this. So this means that 1 gram of coal release 22.3 kilojoule of energy. Okay, yeah, something that I didn't mention is the energy is released. Okay, so Q will be negative, so the fuel value is the energy that's going to be released by the coal. Using the reaction enthalpy data shown below, determine the heat change in this situation. So now what you will see is that we have heat associated to the reaction. Okay, delta H is the enthalpy of the reaction. So this is the heat, it's similar to Q. And because your enthalpy for the reaction is negative, we know that this process is exothermic. The heat is lost by the system. Okay, the energy is lost. Therefore, so again, the energy is lost by the system, and that's why we have a delta H that is negative. So we're going to write, you remember from the prior chapter, our mole recipe. And now we will just expand our mole recipe. The equation below states that 511.3 kilojoule of heat will be released when 1 mole of tin react with 2 mole of Cl2 to form 1 mole of SnCl4. So the mole recipe becomes that 1 mole of tin is equal to 2 mole of Cl2 is equal to 1 mole of SnCl4. And when this process happens, minus 511.3 kilojoule of heat is released. So, in the first question, we're given 0.1948 mole of tin, and during the entire problem, we want to determine the heat change. Okay, so we're looking for energy released or absorbed, heat change. This is what we're looking for. So here, therefore, we start with 0.1948 mole of tin. What do we want to do? We want to get the energy, and we want to cancel the mole of tin. Take a look at your mole recipe. For every mole of tin, this much energy is released. For every 1 mole of tin, that's 511.3 kilojoule of energy released. The mole of tin cancels, and we're left to 4 sig figs with minus 99.60 kilojoule of heat released when 0.1948 mole of tin react. What if this time 19.72 gram of chlorine gas reacts? Remember that chlorine gas is diatomic, it's Cl2. We have 19.72 gram of Cl2, and we only have a mole recipe. Remember that this is the golden unit for the chemist, so our first step will actually to convert our gram of Cl2 to mole of Cl2. That's our step 1. And once we have done this, we will be able to use our mole recipe, where we now cancel our mole of Cl2 and we convert into energy. Second step, which has to do with the mole recipe. So what do we have here? We're looking for the molar mass of Cl2. Using your periodic table is 2 times the molar mass of Cl. So it's equal to 70.90 gram per mole. One mole of Cl2 is 70.90 gram of Cl2, and per our balance equation up there, if I can just remove this now. Okay, this time it's 2 mole of Cl2 that release the 511.3 kilojoules. So we're going to need to place a 2 here for 511.3 kilojoules following the recipe. Let's take a look and see that our unit cancel properly. The gram with the gram, the mole with the mole. We converted grams of chlorine gas into kilojoules. And when you plug this into your calculator, you get to 4 sig figs minus 71.11 kilojoule of heat released when 19.72 gram of chlorine gas react. Question C. This time we're given 12.0 gram of tin 4 chloride. Remember that this tin 4 chloride is SnCl4. We're going to have to start with the 12.0 gram of SnCl4. We're going to use the mole recipe, but as named, the mole recipe involves mole. So we need to convert it into mole first before we can use our expanded mole recipe. Cancel the gram of SnCl4. 1 time the molar mass of Sn and 4 times the molar mass of Cl give us a molar mass for SnCl4 of 260.51 gram per mole. Then we will use in our second step our mole recipe to cancel the mole of SnCl4 and convert to kilojoule. Again, check that your unit cancel properly and fill in your blank. The molar mass is for 1 mole of tin 4 chloride, 260.51 gram, and the mole recipe states this time that the 511.3 kilojoule are released for 1 mole of SnCl4. So it's going to be a 1 here and minus 511.3 right there. Plug this into your calculator, and 3 sig figs minus 23.6 kilojoule of heat are released when tin and chlorine react to form 12.0 gram of chlorine gas. Let's take a look at problem 3 now. You're told that calcium oxide, CaO, is the major component of cement mix, that manufacturers produce this compound by decomposition of calcium hydroxide as shown in the equation below. We're going to use the reaction enthalpy. Here is the reaction enthalpy. to calculate the energy that is required to produce 1 kilogram of calcium oxide by this process. So what is this reaction information giving us? We have here a positive enthalpy, reaction enthalpy, therefore the process is endothermic. The heat needs to be added to the system in order for the decomposition reaction to happen. Okay, so the heat needs to be added to the system. We will be able to write our mole recipe. Remember, we always write mole recipe. 1 mole of CaOH 2 time equal 1 mole of H2O equal 1 mole of CaO, expanded mole recipe, because when this reaction happen, in order for the reaction to happen, 108.5 kilojoule of energy needs to be input into the system. So what's the given and what's the desired? Well, we're given 1 kilogram of calcium oxide, and we want to know how much energy does this require. So we're going to start here to end here. So let's start in our conversion steps with 1 kilogram of calcium oxide. It's 1, so this number is exact. Okay, it's 1, so that's why this make it an exact number. Then what do we have? If we look, the mole recipe, okay, give us the relationship between mole of calcium oxide and the energy. So our first step, we'll get the golden unit of the chem is the mole. The mole is associated to the mass by the molar mass, okay? And what is the molar mass of calcium oxide? Per periodic table is 1 time the molar mass of A plus 1 time the molar mass of O. So it's 56.08 grams per mole. Gram, notice, okay? Here I have grams, here I have kilograms. So my first step, if I want to be able to use the molar mass as a conversion factor, is to convert kilogram of calcium oxide to gram of calcium oxide. Once I have gram of calcium oxide, I can convert 2 mole of calcium oxide by using the molar mass of calcium oxide, and finally using the expanded mole recipe, okay, I will be able to cancel my mole of calcium oxide and convert to kilojoules. Let's fill in the blanks. We know that a kilogram is 10 to the 3rd gram. We know now that because we just calculated the molar mass, that 1 mole of calcium oxide is 56.08 gram, and our expanded mole recipe tells us that for every mole of calcium oxide, 108.5 kilojoule of heat is required. We're going to plug this in our calculator, and we'll get to 4 sig figs 1,935 kilojoule of heat energy is required to produce 1 kilogram of calcium oxide by this process. Why 4 sig figs? Because the 1 is exact. This conversion factor as well is exact, the use of prefixes. This conversion factor, molar mass as 4 sig fig, and this conversion factor here as 4 sig figs. Therefore, our answer is given to 4 sig figs. Let's go to the back of the page now, where we have here an acid-base neutralization reaction between hydrobromic acid and potassium hydroxide. We're told that this process is exothermic, confirmed here by a negative delta H. And we want to know, so we'd like to know how many grams of HBr can be neutralized when this much heat is released in the process. So we're going to start here. We know that the heat is released, so it's negative. Negative 119.0 kilojoule is our starting point. And we'd like to end here with grams of HBr. We're going to write our expanded mole recipe now. 1 mole of HBr equal 1 mole of KOH equal 1 mole of KBr equal 1 mole of H2O. Release 585.8 kilojoule of heat. Again, we're going to start with our 119.0 kilojoule. That's our starting point. What we want at the end is gram of HBr. So our goal is to go to the golden unit for HBr by using here our mole recipe. We can cancel the kilojoule and convert to the golden unit for HBr. Why HBr? Because this is what we're looking for. And finally, we know how to easily go from mole of HBr to gram of HBr by using the molar mass of HBr that can be calculated from the periodic table. 1 mole of HBr, 1 time molar mass of H plus 1 time molar mass of Br is 80.91 gram. And the expanded mole recipe tells us that for every mole of HBr, this much energy is released. For every mole of HBr, minus 55.8 kilojoule of heat are released. Check that your unit cancel properly, and you get to 3 sig figs 173 gram of HBr being neutralized. Last problem for this worksheet. A chemical manufacturer needs to neutralize a mixture containing 25.2 kg of sodium hydroxide by reacting it with an excess of hydrochloric acid. The chemical engineers estimate that once filled, the insulated reaction vessel will have heat capacity of 318.5 kilojoules per degree Celsius. Based on this data, determine the amount of heat released by this reaction. If the neutralization starts at the temperature of 30.0 Celsius, how hot will the reaction vessel get? So, there's a lot of information in that problem, and we need to take our time to analyze the problem. You are given a picture with the problem that might help you to understand what's going on. So first of all, take a look that we are given a heat capacity. If we are given a heat capacity, it means we are in presence of a bomb call. If we are in presence of a bomb calorimeter with a heat capacity C of 318.5 kilojoule per degree Celsius. So, the first problem consists of, based on this data, determine the amount of heat released by the reaction. So this is question number 1. We have a bomb cal with a heat capacity of 318.5 kilojoule per degree Celsius. Okay? And we know that we are in presence of 25.2 kilogram of sodium hydroxide. And we're given the reaction that is happening into the system. Okay? So remember, what did I tell you? That every time you're given a reaction, we're going to write the mole recipe, the expanded mole recipe. So we have 1 mole of HCl equal 1 mole of NaOH equal 1 mole of NaCl equal 1 mole of H2O. This process is exothermic and releases 55.8 kilojoule of heat. We know that the bomb cal contains this much of sodium hydroxide, and we want to know how much heat is released by the reaction, okay? And we know that for every mole of sodium hydroxide, this much heat is released. So our job will be to, in the first question, to find how much heat will be to go from our 25.2 kilogram of sodium hydroxide, 2 moles of sodium hydroxide, so we can find the amount of heat released by the reaction, okay? So let's start. We have 25.2 kilogram of sodium hydroxide here. You guys know that we cannot work with kilogram due to the molar mass. That's going to allow us to get the golden units, so we need to cancel the kilogram and convert to gram. Once we have this, we can use the molar mass of sodium hydroxide to cancel the gram of sodium hydroxide and convert to mole of sodium hydroxide. And finally, we can use the expanded mole recipe to cancel the mole of sodium hydroxide and convert into heat. Check that the plan works and the unit cancels accordingly, and then we will fill in our blank. The expanded mole recipe tells us that for every mole of sodium hydroxide, minus 55.8 kilojoules of heat are released. Chapter 2 tells us that 1 kilogram is 10 to the third gram, and using our periodic table, we can determine the molar mass of sodium hydroxide. Since it's 1 time the atomic mass of Na plus 1 time the atomic mass of O and 1 time the atomic mass of H, 1 mole of NaOH is 40.00 gram of NaOH. Plug this into your calculator, okay, and you will get to 3 sig figs that minus 3.52 times 10 to the 4th kilojoules of heat are released. So where do we see this on the diagram? It's this arrow that you have right there, okay? When you have in there your 25.2 kilogram of sodium hydroxide, and when the manufacturer neutralizes the mixture, then heat will be transferred to the bomb cowl, because here we have our bomb cowl, okay? And how much heat will be released by the reaction? Minus 3.52 times 10 to the 4th, okay? Again, this is the energy released by the reaction. This heat released by the reaction will be, as I mentioned, transferred where? To the bomb cowl. Therefore, the energy will be absorbed by the bomb cowl. And how much energy will be absorbed? Plus 3.52 times 10 to the 4 kilojoule. Okay, this is how much the bomb cowl will be absorbing. Since this is how much heat is released by the reaction, and because of the transfer, and energy cannot be created or destroyed. So what is question number 2 then? If we look up there again, question number 2 is if it starts at this temp, so if the neutralization starts at a TI of 30.0 Celsius for the bomb cowl, how hot will the reaction vessel get? So this is how hot, so what's TF? That's the question number 2. So let's talk about question number 2. We are in presence of a bomb cowl that has a heat capacity of 318.5 kilojoule per Celsius. Because it's a bomb cowl and because we have a C, the equation we're going to be using is Q equals C delta T. And therefore we have again 2-step problem. Okay, we know this and we know how much heat is absorbed by the bomb cowl. So our first unknown is delta T. Delta T is our first unknown. We don't want to look for TF yet. So we're going to divide on each side by C to solve for delta T. Delta T is equal to Q over C. Therefore, delta T is equal to 3.52 times 10 to the 4th kilojoule over 318.5 kilojoule per Celsius. Notice that the kilojoule canceled and you're left with a change in temp of 110.37 degrees Celsius. Okay? And now we can solve for our real unknown. We know that delta T is TF minus TI. Ti is given in the problem as being 30.0 Celsius. This is the initial temperature of the bomb cal. And we want to know how hot will the reaction vessel get, knowing that we started at 30.0. Well, our delta T here is right there. We're going to add Ti on both sides. So we get TF equal delta T plus Ti. TF equal 110.37 Celsius plus 30.0 Celsius. Sig figs wise, what happened? We have to go back and track everything. If we look at the delta T here, 3 sig figs over 4 sig figs. It's a division, so we go with the least amount of sig figs, so only 3. Therefore, only these numbers count into delta T. Only these numbers count into delta T. When we solve for TF, we're doing a addition. So we go by decimal places. But this number has actually no decimal places since it only has the 3 sig figs that are 110. Therefore, our answer will be to no decimal places. The reason why is again because of the sig figs here. Since your delta T only has 3 sig figs, only these 3 numbers count. So only these 3 numbers count. These 3 numbers have no decimal places, so even if I had a number with a decimal place, I don't really know what's the number after the 0 point, so I can only give my answer to no decimal places. And the final temperature to the correct number of sig figs is 140 points Celsius or 1.4 times 10 to the 2nd degrees Celsius.